Welcome to today's class. We will be looking at deep learning. In this lecture, we will have a recap of artificial neural networks. We will discuss limitations of ANNs, and in that context also see why deep neural networks became very useful. We will discuss autoencoders, restricted Boltzmann machines, and then get into the practical aspects of deep learning. We discuss the concept of an artificial neural network which has three layers: an input layer, a hidden layer, and an output layer. We showed that a network with such three layers can learn any arbitrary function. For example, such a network could separate data like these red colored samples and these orange colored samples from each other. These samples cannot be separated by a straight line, so a perceptron is not suitable for separating this data out. But a three-layer neural network can definitely create a classification function which can separate the data. Even if the data is arbitrarily distributed, we saw that by increasing the number of nodes in the hidden layer, even this data can be classified. For example, in the case of this neural network, we have 4 input nodes, 2 hidden nodes, and 1 output node. The output of this hidden node is given by this equation. This hidden node is behaving as a perceptron which is taking as input these 4 values from these 4 input nodes, performing a weighted sum of those, adding the bias to it, and applying a squashing function on it. In the same manner, the output of this hidden node is given by this equation. The output node behaves as a perceptron that takes as input h1 and h2. And the equation of the output node is given by y is equal to f of the weighted sum of h1 and h2 plus a bias of the output node itself. This layering allows the output to represent a very complex combination of the input values. And this complex combination allows us to represent arbitrary surfaces which can separate different kinds of distributions of data. So even highly complex distributions of data can be represented by the neural network having 3 layers. The artificial neural network is suitable for a wide range of machine learning applications because of its ability to model arbitrary surfaces. However, it is nowhere close to the kind of connections that are made in the brain. So for example, if you look here, the neuron F, G, E, and A form a closed loop based on several of their synapse and dendrite connections. So for instance, there are connections here between F and A. E and A seem to be connected here. G and E are connected here, and G and F are also connected. Similarly, G is connected to H, H is connected to D, D is connected to E. J is connected to H, which in turn is connected to D, D is connected to B, B to C, and C to this particular neuron. And this neuron is connected to J. These kinds of loops and highly complex connections are not possible in an artificial neural network. The artificial neural network has multiple layers arranged sequentially. So in this example, we have an input layer, a hidden layer, and an output layer placed one after the other to have a total of 3 layers. There might be a different situation where we have an input layer, a hidden layer, another hidden layer, and an output layer to have total of 4 layers in an ANN. But the differentiating factor between the brain and the ANN is, in the artificial neural network, the direction of signal flow is always in one side. So for instance, the signal flows from an input to multiple hidden nodes, then from a hidden node to multiple output nodes. So one layer passes on its output to the next layer. It never happens in an artificial neural network that you would have the output signal being passed back to the hidden layer or the output signal being looped back to itself. So you don't have any connections in the reverse direction. Also, you don't have any nodes that are getting switched on or switched off. Whereas in the brain, you have a lot of self loops. In an artificial neural network, the input layer passes on its values to the hidden layer. All the nodes in the hidden layer would compute their output values and pass these values to the output layer. Then all the nodes in the output layer will compute their own values and pass the values as final output. Whereas in the brain, this kind of sequential processing does not take place. It has been shown using various imaging techniques that different nodes in the brain or different neurons in the brain can fire at arbitrary times. There is no guarantee that a particular node should fire first and then only a next node should fire. Any node can fire at any given point of time. So several nodes can be active at any given point of time. Several nodes are also similarly inactive. But that's not the case in an ANN. In an ANN, all the hidden layer nodes must fire together. For instance, if this neural network had two hidden layers, then all the hidden nodes in this layer would fire first, give their output to the next hidden layer, then that hidden layer would fire, generate its outputs, and then those outputs will pass on to the output layer. The output layer nodes would then compute the final output. So there is a distinctly sequential processing in the artificial neural network. The brain, therefore, is a much more complex structure where billions of neurons are connected together to generate interesting and intertwined patterns. The ANN, in comparison, is a sequential structure. And therefore, while it's useful in a lot of machine learning tasks, it has certain inherent limitations. Deep learning emerged as a solution to these limitations. Let's look at what some of those limitations are and how deep learning can circumvent them. A primary drawback of artificial neural network is that it requires training samples and feature engineering for every new task, whereas humans typically learn a new but similar task much faster. So for instance, if a human being has already seen these alphabets and has already learnt how to recognize these alphabets as an A, then when this particular sample is shown, the human will most likely be able to recognize that this is also the alphabet A, even though the shape is slightly different. In fact, the human will be able to say that this shape of A is very similar to this shape of A. A child who is learning alphabets for the first time might get thrown off if it is presented with this alphabet. But the child would eventually also recognize that this alphabet is the same as these alphabets A, but the amount of time to recognize this alphabet, while it's slightly longer, is not the same as to learn the original alphabet. From a practitioner's perspective, or from the perspective of someone who needs to use an ANN, the ANN requires feature engineering for every task. So for instance, if your input is already not in this format, that is, it's not in a structured data format, the input data is not real numbers, but it is unstructured data like this. So if your data is images or it is text documents, you would first need to take that data and convert that using some feature engineering process into features and a class label. This structured data can then be used to train an ANN. A properly designed deep neural network will not require feature engineering. Unstructured data, whether in the form of text or images, can be directly passed on to the neural network. Please note that both are artificial and both are networks. One could argue that a deep neural network is an artificial deep neural network. There are, however, some additional differences. An ANN has generally one or two hidden layers. Deep neural network have several hidden layers, typically 5 to 20 or even more than that. An artificial neural network is trained using the backpropagation algorithms. That is, all the layers are trained together. In the case of a deep neural network, individual hidden layers can be trained separately using autoencoders or RBMs. In the case of an artificial neural network, if the dataset changes, feature engineering has to be done once again. Oftentimes, the entire network also changes. The network architecture would be different. That means the number of hidden nodes, the number of output nodes could be different. In the case of a deep neural network, even if the dataset changes, certain layers can be reused using a concept called transfer learning. A network trained for one problem in the case of an ANN cannot be used for a different problem. Whereas in the case of a deep neural network, hidden layers that are trained for one problem can sometimes be used in a different problem. We will now look at how autoencoders can be used to build deep learning networks. The goal of an autoencoder is to create a hidden layer that can learn the compressed representation of an input signal. This is accomplished by creating an artificial neural network with 3 layers, an input layer, a hidden layer, and an output layer, and by training it on an artificial task. After the training is complete, the output layer is removed and only the hidden layer and the input layers are retained. An example fake task to train an autoencoder could be the denoising task. In denoising, for every sample xk, we would select a few of the features randomly. Let us say we select 3 features randomly. To these 3 features, a small amount of noise would be added to create an approximate sample xk bar. This noisy or approximate sample xk bar would be fed at the input, and the original feature vector xk would be expected at the output. And training is done using backpropagation. The noise could be Gaussian, setting a percentage of the inputs to 0. That means the 3 features that we selected, those would be set to 0. Or it could be adding salt and pepper noise. For example, for this data set, in the case of a backpropagation algorithm that is designed to do classification, we would build a neural network that looks like this. There would be a number of input nodes which are equal to the number of features here. So since we have 5 features, the number of input nodes would be 5. There would be a few hidden nodes and a single output node. This network would be trained by using x1, x2, x3, x4 and x5 as input features and the label y as an output value. In the case of an autoencoder, each feature vector or each training sample is taken, noise is added to the training sample, and this is used as data to train this kind of a network. For this kind of a network, the number of output nodes is equal to the number of input nodes. In our example, the training data set has 5 features, therefore the number of input nodes would be 5 and the number of output nodes would also be 5. The number of hidden nodes would be empirically determined. Now let's say we fixed a certain number of hidden nodes. Let's say we fix the hidden nodes to be 3. The network configuration would therefore be 5 nodes in the input layer, 3 nodes in the hidden layer, and 5 nodes in the output layer. And this network would be trained in the following way. The first feature vector is shown here. We randomly select few of these features. So in this case, we have selected 2 features, and noise is added to these features. Therefore, the 0.0097 here has become 0.00297 in x1 bar, and 0.6653 has become 0.6643. This noisy sample or approximate sample x1 bar is fed at the input. And during backpropagation, x1 is expected at the output. The difference between these 2 networks is that during training of these networks, the feature vector is fed as input, and the true value that is expected at the output is this label value. And this is used in backpropagation. While training this network, the input is this noisy data for each training sample, and the true value that is expected at the output is the original feature vector. For networks like these, which are typically artificial neural networks that have been designed for, let's say, a classification task, the error function would look at the difference between the true value and the predicted output value of a class label. The true value of the class label is given from your training dataset, the y value from the training dataset. And the predicted output value is obtained by passing an input feature vector to the neural network and recording the output values. While training an autoencoder, the error function looks at the difference between the original feature vector and the predicted value of the feature vector. The predicted feature vectors are obtained by passing these noisy feature vectors or approximate feature vectors through the input and recording the values obtained at the output. Let us say we've trained our autoencoder for several iterations and we got to a situation where the error rate is low. A low error rate indicates that the output values are equal to the original feature vector values. If we recall, our autoencoder was being trained by using these approximate or noisy feature vectors. So if our autoencoder is generating a low error rate, that means our autoencoder has trained to remove the noise from these noisy feature vectors and perfectly predict the original feature vectors for every training sample. In the subsequent slides, we will represent autoencoders with this block. So for instance, this block represents the input nodes in the autoencoder. And the number of nodes is indicated by this number I. This block represents the hidden nodes of the autoencoder and the number of nodes is J. And this block represents the output nodes of the autoencoder and the number of nodes in the output is equal to the number of nodes in the input. The output of each node in the hidden layer is indicated by this function. And the output of each node in the output layer is indicated by this function. For example, in an image processing problem, an autoencoder may be trained by taking several images, adding noise to these images, feeding these noisy images as input, and during training, the original image is expected at the output layer. Here, we are making an assumption that each image has a size of 100 by 100. Therefore, the number of input nodes for the autoencoder would be 10,000 nodes. An image with noise is fed to the input nodes in the following manner. Row 1, column 1, that is the first pixel in the image, is fed to node number 1 in the input. Pixel at row 1, column 2 is given as input to node number 2 in the input block. Row 1, column 3 would go as input to node number 3 in the input layer. And so on and so forth. Each of the 10,000 pixels would correspond to one node in the input layer. In this example, there are 500 nodes in the hidden layer. This is an empirical parameter that is typically set after experimentation. The output layer has the same number of nodes as the input layer, that is 10,000 nodes. The noise that is used to train this autoencoder can be of different types. Salt and pepper noise, which is like this. This is the original image and this is the image with salt and pepper noise. Gaussian blur. This is an input image, this is an image with Gaussian blur added to it. And some pixels in this image have been set to 0 and there is also some blur in this image. After the training is complete, what would the hidden layer learn? The output of each node in the hidden layer is given by this equation H. The output of each node in the output layer is given by this equation. The weights Vij along with the weights Wjk represent the functions which can remove the noise from an input and recreate the original noise-free output values. So what does the hidden layer itself learn? The hidden layer in a sense also learns a part of the noise removal. When would we say that an autoencoder is well trained or an autoencoder has some practical use? Let us say an autoencoder was built that could take as input an image of 3 sheep standing together, for example this image, with some noise added to it, and it could recreate the image of the sheep without that noise. But it could only remove noise from that image of the 3 sheep standing together, and it wouldn't work on any other image at all. So for instance, you could take this image, add all kinds of noise to it, feed it as input, and the autoencoder will give you this image as the output. Would such an autoencoder be of any practical use? That autoencoder would work only on one image, so it's of no practical use. Therefore, our autoencoder should be able to work on a variety of images. The second is, the autoencoder should be able to remove noise of different types. Ideally, we'd like to have an autoencoder which can remove salt and pepper noise, blur, or missing pixels. Let us say we have trained such an autoencoder. Our autoencoder is able to handle a variety of images, and it's also able to remove different kinds of noise from the input image and generate images without the noise in them. Let us say we have such a well-trained autoencoder, A1 here as an example, and it is able to remove a variety of noise from a variety of images. What should be the output if the amount of noise is less than what it was trained on, or if the amount of noise had a range? So for instance, here you have an input image with more noise, there is less noise in this image, and there is even lesser noise in this image. If this network is indeed well trained, we would expect that the output is the image without noise in it. In effect, the autoencoder A1 is able to retain parts of an image that are useful for perception and remove those parts of the image, such as this noise, which is not useful in the perception task. We have seen that the autoencoder that we just designed, the autoencoder A1, is able to remove parts of the image that are not useful for perception, like these noise, and it retains parts of the image that are useful for perception while creating the output image. Let's examine what is the output from the hidden layer and the output layer. The output of each node in the hidden layer H1, that is this layer, is given by this equation, where Vij are weights of the hidden layer. The output of each node in O1 is given by this equation. OK in effect represents each pixel of the output image. Remember, this output has 10,000 nodes, and in our example we had a 100 by 100 image. So OK represents each pixel in the output image, and this is given by this equation. Wjk are weights of the output layer, and Hj is the output that is obtained from the hidden layer, which is given by this function. Now, after the training is complete, these weights Vij and Wjk do not change. So from one image to another image, the values of the weights don't change. So the values of Vij and Wjk do not change because the training has been completed. These weights are changed only when the training is going on. So what if we stored these values Hj, that is output from the hidden layer, and we computed this function OK tilde, which is essentially the same as this function, except that Hj has been stored and we computed this at a later time. So the weights Wjk are the same. Now can we say that this OK tilde is the same as OK? Yes. Obviously, if Hj is the same and these weights Wjk did not change, then essentially these two functions are giving the same result. Does this mean that for a given input image, instead of computing the output image completely, can we store the hidden layer values? That means, can we store the 500 values that come from the hidden layer and use that at a later time to recreate the output image? Yes, we certainly can. And because we can do that, does that mean that the hidden layer is representing all the information that is necessary to recreate useful features in the output image? Yes. So in other words, we can say that the hidden layer represents a compressed form or the useful information from an input image. Now let us say we took such an autoencoder A1 which was trained, and now we feed different kinds of images. We feed around 50,000 images one after the other, and we record the output at the hidden layer. So for instance, for image number 1, we would get a 500 valued feature vector which would represent the compressed form of this image. Similarly, for image number 2, we would get 500 floating point values which represent the compressed form of this image, and so on and so forth. If we were to use the output layer on these values, we would be able to recreate the original image. Therefore, we can say that each of these feature vectors represents a compressed form or all the useful information from these images. Autoencoder A1 was trained to take as input images that contain noise in them, and in the output layer remove this noise. Let us train an autoencoder A2 which has a slightly different configuration and operates on the features that are obtained from hidden layer H1 of autoencoder A1. Autoencoder A2 has the following architecture. The number of inputs are 500. Note that the output from hidden layer H1 of autoencoder A1 is 500 features. So the input of autoencoder A2 has 500 nodes. The hidden layer of autoencoder A2 has 150 nodes, and the output of autoencoder A2 has 500 nodes. The input of autoencoder A2 will be this table with a noise added to it. That means for each sample, for each feature vector, we would add noise to some of the columns, and that would be input to the autoencoder A2. The autoencoder A2 would be expected to remove this noise and generate the original feature vector. So for instance, this table, which is the expected output of autoencoder A2, is the same as this table. And this table is this table with noise added to some of the columns. After the training of this autoencoder A2 is finished, what will the autoencoder A2 learn? The autoencoder A2 will learn to remove noise from these 500 features if there is any noise in them. So for some reason, if autoencoder A1 was generating noise in this hidden layer for a given image, for a given input image, if autoencoder A1 was generating a noisy output from its hidden layer, autoencoder A2 would be able to remove that noise. We could also say that autoencoder A2 and the hidden layer H2 is learning a compressed representation of the input to autoencoder A2. For autoencoder A1, after it has finished training, we made an argument that the output of the hidden layer H1 is storing a compressed representation of the input image. We can make the same argument for autoencoder A2 and the hidden layer H2. The autoencoder A2 and hidden layer H2 is operating on the 500 features which are obtained from the hidden layer of autoencoder A1. By extending the argument that we made on this slide to autoencoder A2, we can conclude that the hidden layer H2, which has 150 nodes, is learning a compressed representation of its input. And the input to hidden layer H2 is the output from hidden layer H1 of autoencoder A1. Therefore, the hidden layer H2 of autoencoder A2 is learning a compressed representation of these feature vectors. We had earlier shown that you can take an image collection, pass it through autoencoder A1 with its output layer removed. We recorded for every input image the output of the hidden layer. So for each input image, we have 500 features. This table H1 is the same as this table. So H1 contains one set of features for each input image. So sample number 1 corresponds to one image and has 500 values. Sample number 2 corresponds to the second image and has 500 values, and so on. If we take this table, input that to autoencoder A2, which has been fully trained, pass it through the input layer and then the hidden layer, but remove the output layer. The values that we'll record are the values from the hidden layer H2 of autoencoder A2. For each input image, we have a feature vector here. And for each of these feature vectors, that means for sample number 1, we pass 500 values through the input layer of A2 and through the hidden layer of H2, and we will get 150 floating point values from hidden layer H2 of autoencoder A2. So the output of hidden layer H2 would be this equation, where Vij corresponds to the weights of the hidden layer H2 of autoencoder A2. So for each sample in the H1 table, that means for each sample in this table, or rather this table, we will get one vector having 150 floating point values. We know that these 150 feature values are a compressed representation of these 500 feature values. By the arguments that we made earlier, we know that these 500 feature values are a compressed representation of the input image. By extension, we can say that these 150 feature values that are obtained from hidden layer H2 of autoencoder A2 are therefore a compressed representation of the input image. It can be shown that the 150 feature values obtained from autoencoder A2 hidden layer H2 can be passed through the output layer O2 and output layer O1 of autoencoders A2 and A1 respectively to recreate the original image. Using this argument also, we can say that each of these feature vectors is a compressed representation of an image and stores the useful features in the image. We have seen that we can train an autoencoder A2 having the configuration 500 inputs, 150 hidden nodes, and 500 nodes in the output by training on the hidden value output of autoencoder A1 on a set of images. The output of hidden layer H1 of autoencoder A1 on a large number of images was collected. Noise was added to this output, fed as input here. The autoencoder A2 was trained to remove the noise from this input and recreate the output H1 of autoencoder A1. Similarly, we can train another autoencoder A3, whose configuration could be input containing 150 nodes, hidden layer containing 240 nodes, and the output layer containing 150 nodes. The number of inputs in autoencoder A2 was 500, which is equal to the number of nodes in the hidden layer H1 of autoencoder A1. Similarly, the number of inputs in autoencoder A3 is 150, which is equal to the number of hidden nodes H2 in autoencoder A2. So how do we train autoencoder A3? Autoencoder A3 is trained by taking the output from hidden layer H2 of autoencoder A2. We have seen in a previous slide that the output of hidden layer H2 of autoencoder A2 is obtained as a vector of 150 feature values. These 150 feature values represent compressed form of an input image. This table H2 is taken and noise is added to some of the columns. This is the table H2 with noise added to some of the columns, and this is the original table H2. So autoencoder A3 is trained to take as input the table H2 with some noise added to it and recreate the original table H2 without any noise in it. After autoencoder A3 has finished training, what can we say about its behavior? Also, what does the hidden layer H3 represent? Going by the arguments that we made for autoencoder A1 and autoencoder A2, we can say that autoencoder A3 would also have learned to remove noise from its input. The hidden layer H3 therefore would remember to keep important parts of its input and remove the useless parts or ignore the useless parts. In the previous autoencoders, we had made an argument that the hidden layer was representing a compressed form of the input. But if we notice, autoencoder A1, hidden layer H1 had 500 nodes, which was less than the number of input nodes. Autoencoder A2 had 150 hidden nodes, which was less than the number of its input nodes, which were 500. But autoencoder A3 has 240 nodes. This is more than the number of nodes in its input. So the hidden layer of autoencoder A3 is not necessarily learning a compressed representation, but it is also learning to remove any kind of noise from its input. So we can also infer that it is not necessary to build autoencoders that had number of hidden nodes lesser than the number of input nodes. It's also possible to have the number of hidden nodes greater than the number of inputs. And even such an autoencoder would be able to remove noise from the input and learn the useful parts of the input and ignore the non-critical parts of the input. In a similar fashion, multiple autoencoders could be trained. We have seen that multiple autoencoders can be trained on a fake task, namely removing noise from input data. And in this process, they can be trained to retain only useful parts of an input signal. This allows us to come up with representations of features of an input image. After training such autoencoders, the autoencoders could be stacked together to generate features of different sizes. For instance, the hidden layer H1 from autoencoder A1 and its input layer are placed here. When an image is input to this layer, these two layers in combination would generate 500 features from that input image. Now the hidden layer H2 from autoencoder number A2 is placed here. The hidden layer H2 can take these 500 values as input and generate 150 features. The hidden layer H3 trained from autoencoder A3 is placed here after hidden layer H2. The 150 features that are coming from hidden layer H2 pass into hidden layer H3 to generate 240 features. This is possible because hidden layer H2 has trained on the features that were output by hidden layer H1. Similarly, hidden layer H3, or rather autoencoder A3, has trained on features that were output by hidden layer H2. Similarly, you could build another autoencoder A4, which has 40 nodes in the hidden layer, 240 inputs in the input layer, 240 output nodes in the output layer. And when you train the autoencoder A4 on data coming in from autoencoder A3, hidden layer H3, this particular hidden layer H4 would also be able to represent the features that are coming in from hidden layer H3 and translate them into 60 features. In this way, you could build multiple hidden layers, stack them together, and extract different kinds of features from an input image. Let us assume that a system was built with 5 such hidden layers being stacked together. Each of the hidden layers would have been trained by using an autoencoder. And let's assume that hidden layer H1 had 500 nodes, hidden layer H2 had 150 nodes, H3 240 nodes, H4 60 nodes, and H5 100 nodes. If we pass our dataset of images through the input layer, the result that we obtain at the hidden layer H5 would be 100 features long. So for instance, for the first image, we would get a feature vector that has 100 features, or rather 100 floating point numbers. Similarly, for image 2, you would get another feature vector having 100 features, and so on for our entire data set. Let us say our task is to classify images as fighter jets versus commercial jets. We would collect a data set of such images, pass each of the sample image through this layer, and generate a set of feature vectors. So for instance, let's say we collected 2000 images. We would take each image from the dataset, pass it through the input layer, then hidden layer H1, H2, H3, H4 and H5, and get the feature vector for that image. So for instance, the first image would generate 100 floating point values which form the feature vector for that image. Similarly, the second image, when passed through this entire stack of hidden layers, would generate 100 feature values which form its feature vector, and so on for our entire dataset. So if we have 2000 images in a dataset, we'll get a set of 2000 samples, each sample containing 100 features. This dataset can also be associated with a class label where a 1 would indicate that it is a fighter jet and a -1 indicates that it is a commercial jet. This labeling needs to be accurate, and therefore one could do it manually or use some deterministic technique to ensure that the labels are not wrong. We have used a stack of hidden layers and this repository of fighter jet and commercial jet images to generate a dataset containing feature vectors for each of these images with the associated class label. Now this data is of a format that can be fed to an artificial neural network. We can build an artificial neural network having the configuration 100 input nodes, 20 hidden nodes, and 1 output node, and this should be able to take as input these feature values and generate our label +1 for a fighter jet and -1 for a commercial jet. The ANN can be trained using this dataset. If we figure out during training that this ANN is not converging, we can potentially change the number of hidden nodes, or we can change this dataset. We can increase the number of samples in this dataset. Instead of selecting 2000 samples, maybe we could use 4000 or 5000 samples. All that we would need is to collect more samples of fighter jets and commercial jets, extract features using this stack of hidden layers, and label the data. If after a few trials we start getting good accuracies from the ANN on this dataset, we can combine these stacks of hidden layers with the ANN to generate a classifier that can differentiate fighter jets and commercial jets. The final architecture of our classifier would be built like this. The input layer would be I1 taken from the autoencoder A1. The hidden layer H1 would be taken from autoencoder A1. This would be connected to hidden layer H2 taken from autoencoder A2, and so on. The hidden layer H5 output would be fed to the neural network that we trained in the previous slide. This entire architecture would now be able to take an input image which has dimensions of 100 pixels in height and 100 pixels in width. This was the original input that was taken by the input layer I1 of autoencoder A1. The output would be a +1 or a -1. The +1 would indicate that the input image is a fighter jet, and a -1 would indicate that the input image is a commercial jet. The intuition behind this architecture is that several of these hidden layers might learn to extract features from the input image. Some of the hidden layers might learn to remove noise effectively, and some other hidden layers may learn to identify higher structures like rectangles, squares, circles, or triangles from the input image. In general, a stack of properly trained autoencoders and their corresponding hidden layers would be able to generate a rich set of features from the input. The number of nodes in the hidden layer, the number of layers that are used in stacking are all hyperparameters. The training of an individual autoencoder can take a lot of trial and error and significant compute resources. However, it's an important advantage that once these hidden layers are properly trained over a rich set of images, these should be able to extract features for any arbitrary image. It is not necessary that, for example, if you want to extract features from a fighter jet, you need to have images of fighter jets in the dataset that was used to train the original autoencoders. The intuition behind this again is that most image processing tasks need similar features. For instance, to differentiate between buildings and, let's say, grasslands, one could use features such as lines, rectangles, squares, circles, etc. Lines, rectangles, and circles could be extracted from images of buildings and outdoor scenes. If your individual autoencoders have been trained on several outdoor images containing structures such as buildings, sceneries of natural images, forest land, grassland, and let's say a few satellite images, the individual hidden layers should be able to extract features such as lines and circles, rectangles and squares, and so on. Now, airplanes can also be differentiated using lines and circles. Fighter jets contain a certain patterns of lines, triangles, and circles, and commercial jets have these same structures in a different pattern. Let us say we have trained a stack of these hidden layers on images containing buildings. It's not necessary to train these stacks on images of fighter jets. The same stack would be able to extract lines, circles, rectangles, and so on from fighter jets as well, and also from commercial jets. So we can use the same stack as a means to extract useful features for commercial jets, for fighter jets, and for natural images. In the subsequent slides, we'll look at restricted Boltzmann machines and the practical aspects of deep learning.